is Professor Andreas Muller from Johannes Kepler University in Austria. And he does some great work in screw theory. That's how I identify him. He runs his own summer school on screw theory somewhere in Europe every year, I believe. Which I've not attended, but I should. So, without any further ado, let's welcome Professor Euler for his presentation.
It's going to be hard, I know, because we had such a good lunch. And when I came in this morning, I was late, I'm sorry. I first realized this is not going to work for me. Because this screen is too small. That's number one problem. And number two problem, I felt so organized. Combined with the lunch, it might be difficult. So what I did a bit of restructuring of my lecture. As Adjoined was saying, what is this? Anyway. So as Adjoined was saying, we have a summer school actually. It was called, but I don't know what it was called. It was, at least it was on singularities. And it was 2 weeks from now, no, 3 weeks ago. And it was a good success. And what I learned, and now I'm just almost done. What I learned from the summer school, and what I learned actually from, origami, that's good. And what I learned from 5 years teaching Lie groups. And people keep saying, you can't teach Lie groups, right?
It is switch on top, turn it on.
So, right. So, and people keep saying, well, you know, there's screw theory and then even Lie group, whatever Lie group means, right? You can't teach this. I do this since 5 years and it's kind of working. Don't play. And it's kind of working. So what I learned is that at some point everybody kind of understands. And then comes the exam. And then you have questions. So you have this quantity there. It looks good, but in which frame is it actually, represented? And then suddenly it doesn't make sense anymore. And what you realize that people did understand the concept, but did not really understand the technical details. So what I would like to do is to give you an idea what it's all about, and to make you understand the detail. The only detail I would like to convey today, because of the limited time, actually I was hoping for more time, but apparently we only have 100 minutes, is to understand, to make you understand the so-called product of exponentials. So who has heard about the exponential mapping of motion, something like this? Who knows about the product of exponentials for a kinematic chain? 1, 2, 3, 4, 5, 6, this makes 20%. Okay, this is good. What I'm talking about is, what I would like to talk about is actually, because this is a very large figure, right? There's no doubt about it. So these dots here, what is it? Is it joints, probably, I guess? Joints, I guess. Good. But how did you actually model this? And there are two extremes. One is to use this, sine, cosine stuff, that's what we call analytic description. And the other one you can say an algebraic description. So you have polynomials. Whatever you use, and somehow you can get this thing in algebraic terms. So what I would like to do is combine screws and Lie groups to somehow come up with an analytic description. So what's all about them, just because I have to make some pictures, because everybody makes pictures before I come to the formulas, you would like to model these things. And the cars, and even you and me, and human body, and walking machines, and then just whatever it is. Wind turbines, you have flexibility in here, but the basic element is the same. And the basic element is that we have to do with frames, because everything boils down to frames. Whenever you model 3D systems, spatial systems, you have to attach frames to bodies, right? So, and then you have to say, okay, one body is moving relative to another body, even the inertial frame, for example, the dual fixed frame. And then you have to take care about how you model actually this, and how you describe this. And that's what it's all about. And of course, there are other things that we're interested in, which we call linkages, I guess. Because linkages, what's a linkage? Does anyone know what a linkage is? This is something kind of special because it has to do with joints. Because a linkage consists of lower pair joints. That's the only thing. And once you have a lower pair joint, or at least if you are able to combine, if you describe the motion of your joint that you have in terms of 1 degree of freedom screw motions, right? Then you are kind of set bound, because then you can use this formulation that we have here in mind. And of course, there are many things that you can that you're interested in. And the most kind of simple thing is, of course, the open chain, which is in this case a kind of a robotic arm. So, and then we like to do this in a more fancy way, that we put it on a moving platform, and this might even be like an omnidirectional thing, and so on and so on. But it's always the same, because you have joints, and then the joints are somehow lined up with links, and then we consider the links as rigid. Number one assumption. Rigid links, so everything is rigid except the joints, because the joints are moving. But the relative motions, of course, is kind of, we look at perfect joints, so to say. Kinematically, perfect joint means that we have no play, no deformations, and no elasticities, and so on. And just to trace, of course, its stiffness is not, what was it?
Strength.
Correct. Stiffness is not fine, but I'm not jumping to this. And of course, then we are looking into advantageous ways of modeling systems in the sense that we would like to reproduce or to reuse modules. And for example, our humanoid, the humanized humanoid is actually walking as doing something more than walking. There are elements that you always kind of combine again and again. And even look here, we have all these power cubes. I mean, these kind of gear motor units, and we combine them. But if you're not going to this granularity, you can say, okay, there's a leg, and the leg is right on the left side, and so on. Then you have arms, and so on. So we would like to have a modular approach. And this has to do, of course, with how the system is actually structured in a topological way of thinking. And in this case, we have a tree structure. What is a tree structure? A tree structure is that we have maybe, this is, you know what I'm talking about? I mean, say that we take the hip, so the pelvis, right? So we take the pelvis as the initial body, I mean, the body that I start from, and then I can actually reach any body, any joint, by just going somewhere along this, if you want to say, topological graph, right? So this is something here. But they're of course closed loop systems, and this is a nice project that we have. It's called this community tent. I mean, this is nice because you can imagine that we have somewhere in your city, you have a building. That building is changing its shape, just to be cool and be fun. But also to adapt the acoustic properties, to adapt to certain situations. Sometimes you want to have rounded shape, sometimes you want a different thing, and sometimes you want maybe moving, right? That might be interesting. So what we are looking into today is very simple. We look into the motion of those systems. And we have heard about 4 bars, linkages, and then of course we should actually not say what we hardly important. Of course we have to look into the topology. The topology has to be represented in some way. It's not about modeling, right? The topology has to be represented in some way, and then we use this called topological graph. And then we say that we have a certain joint axis. This has to do with geometry. So essentially what we are combining is the topology. That means topology is just saying how is a joint connected to another joint by a link, right? It's just the existence of joints and links, and then the geometry is telling you how these things are actually really positioned in space. And then we have to make assumptions, and the assumptions are, of course, some physical properties. And this has to do, for example, with mass and inertial properties, and maybe a compliance. So we assume rigid links in a moment, and we don't care about dynamic properties. And then, of course, we have what? We have constraints, because, I mean, whatever the coordinates are using, whatever the coordinates are that they're using, for example, joint angles, they, of course, are somehow interrelated by the condition that the loop has to be closed. So we have loop constraints, right? And that makes sense. Of course, you can, if you take that, what's the condition for moving? Why is this mobile? Because the axes are meeting, right? So the axes are parallel. That means they are meeting in infinity. If you take the point where they're meeting at the finite point, then you have a spherical mechanism. Anyway, so the topology is the same, and everything is the same. The only thing is the difference is the geometry. And then, of course, you have these parallel kinematic machines, and then, of course, the topology is a bit different. But that's not really what we're interested in today, because today we're interested in how to actually model these systems in terms of the relative motions of joints. So when I'm saying joints, and then we use orange things here. Lower pair joints. Lower pair joints are very simply described as such that, what is a lower pair joint? It's one where the motion is actually is due to surface contact, right? So whenever you have two bodies, and the motion of the relative motion of the two bodies is due to surface contact, then you can call this somehow a lower pair joint. You have this here, you have the point socket, and you have this here, you have two cylinders sliding on each other. That's not a lower pair joint. This is not a lower pair joint. But you can, of course, construct this as, this universal or joint by again come back to this lower pair, this robotic arm, then of course you see that everything is just, in this case, it's just double joint. This is what we do. We do actually a lot of stuff. You can see this on the YouTube channel. This is optimal control with collision avoidance. So this is real time. I mean, it's not fast forward. This is just as it is in practice. And you can see this is of course highly dynamic in the sense that, it's only those ones. Yeah. In the sense that if you look at the housing is shaking. See, this is shaking here. So it's really dynamically demanding. But of course, they can be dynamic, but at the same time interacting with the environment, either environment or cooperating, so that you can actually generate a certain prescribed force, and this is very interesting stuff. Okay, anyway, so I was actually claiming that you can actually use these, if you would have any theory about local joints, then you can use the theory about local joints of modeling most of the systems, and this is a funny mechanism. If you would like to understand what's happening here, then you have to consider that what's the blue and the red link are parallel that it's to that point. What that means is that the system has to come to rest, and then it can start again. And that was one of the few examples where we have actually a cusp in configuration space, right? So when I say configuration space, I was saying, of course, that all these joint angles, they are somewhat constrained with loop constraints, right? So whatever it is, the solution set, the solution variety of these joint angles, they form the configuration space. Now, this has sometimes, most of the time, this is a nicely behaved space, right? So it's kind of smooth and so on. But at some points, this becomes non-smooth. And the worst case, one of the worst cases, if you have cusp, and this is the case here. It was for a long time. I know that even not understood. Of course, then we have seen this. This is the kaleidoscope. Yeah, we have seen this. But that was just a blinker mechanism that you can fall over. That could be a hinge. I mean, this could be a double joint. That could be, a fold, the paper fold. So, okay, back to the point where we started. It's all about frames, because once you would like to model these systems, and for example, if you use one of these commercial or non-commercial multi-body codes, for example, it's all about frames. I mean, and each body gets one frame. This is the body frame, and maybe the reference frame. And kinematically, a body is, I mean, the motion of a body is described in space, just by the motion of the representing body frame. Okay. Then dynamically, of course, there are properties, mass distribution and so on, relative to a certain frame. This might be in different frame. So you would have a center of mass frame, for example. And then again, if you have a joint, what is a joint? A joint is a relative, it's a kinematic relation relative to two frames. So the number joint here, of course, just says that if you have two frames, there is an axis, and you can just put in one axis, but what you need is two frames. So what you then normally do, you have actually one frame here, one frame here. Let's say it's the that link, and the blue and the red one can only these are called joint frames. Okay, so the joint frames, one here, they have a certain constraint due to the motion, or say the freedom, either freedom or constraint. Okay, so you have for each joint we have two frames, and so it's all about frames. And I would like to have a formulation where we don't need frames. So who knows dynamic Hartenberg parameters? Right, excellent. Who likes them? Good. Who doesn't like them? Who doesn't care? Good. Okay. The point is, they are not nice, I guess. I mean, they are okay, but the time they have been developed, I suppose, is really good. It is still a really good tool, right? So, because what's the advantage of having a certain set of parameters that we agreed upon that you can communicate, right? Because whatever the number, however complicated it is, but if the numbers are the reading and you can convey the reading, the numbers, then you have kind of a standard way of describing systems. The problem is, of course, this is not unique because there are not different versions of these. There's the copy this one, how we can paper from anyway. There are different ways, I mean, different versions of this dynamic parameters. So this is something you can consider. Why did they do it here? Because there are shortcomings. Again, there are shortcomings in the other versions. But then the good thing is that you only need 4 parameters. When you have 4 parameters, each of these parameters describes once again, an elementary motion. So like a 1 degree of freedom motion. That might be either a constant, or let me say a 1-parameter transformation. This could be a constant, this could be a variable. For example, if theta, if you have level joint, for example, then the theta would be the rotation angle, right? And then you can combine all these 4 transformations that are described by the respective parameter, and then you combine and you get this, right? This is well known. Okay. Not nice, because you have to introduce all this. What about if you can say that, okay, so this is it. Yeah, okay, yeah, so is it easy? Well, you can do it. What about if you have this, I just copied this from, in German it says potato selecting machine. So essentially it's a machine that somehow is harvesting potatoes. So now if you look at all these things, I mean all the kinematic pairs here, then and try to find dynamic outcome parameters. Everything is possible, but it's not easy. So maybe there's a better way of doing it. Yeah. But the good thing is, of course, once you have it, then you can combine them. But see how many transformations you have to combine. So one joint is this. So one goes, there's one, the first joint that goes from the frame, from the ground to the first link, and then the second, and so on. You can combine them. Each of them is 4 transformations. So you have essentially 4 times n transformations to do. It's all doable, no problem. If you go, then describe the velocity and acceleration of each of the bodies. Then it becomes a bit messy. But of course, everything is doable, and this is what we're teaching. But maybe there's a better way of doing it. I'm going to jerk this nice. What about this so-called 2-frame transformation? And there's a nice book actually. There's one, for example, John Euler and Armani, they had this nice book. Anyway, so it's just the idea is basic multibody dynamics, I would say. This goes back to the 70s. So as I was saying, the basic idea is so you have the body, and then whenever there is a joint between 2 bodies, you say, okay, we have 2 joint frames. The relative motion of the joint frame is now describing actually what is the possible allowed motion due to the joint. In this case, maybe a double joint. Okay, so and once you have this, then of course you can describe this homogeneous transformation, and the transformation from that frame to the predecessor frame, by 3 transformations instead of 4. One is the constant that just says, okay, how is this frame, the joint frame, on body I located relative to the body frame. And the same, of course, on body I minus 1. So you have that one and that one. So the S, by coincidence, I use the same letter, and actually in the book they call it also ASME, and they call it shape matrix. I'm not sure if this makes sense, but they call it shape matrix. You could somehow describe the shape of the link. Okay, so and then there is the one in between, and the one in between is just the transformation or the relative motion between the 2 joint frames. Okay, and that depends on certain parameter, a certain angle, or whatever the meaning of Q is, and that's fine. Okay, good. Then you can combine them. What about if you were able to actually express the relative transformation by an exponential mapping? This would be, I don't know, maybe it would be nice. So why would this be nice? So what's good about an exponential mapping? It's all about derivatives, because once you have once you have the relative motion, then you would like to know more about velocities and accelerations. Without going into detail what that actually means, but whenever you have an exponential function, right, take the derivative, what you get is an exponential function. That's nice. So it's repeated, right? And this is one of the reasons why this makes life easy. And also the question is, so this is one thing, but what about this y? There's an argument ending it. We didn't talk about this argument, we're going to this in a minute. And I can make the claim now that actually this y, we can actually find this very easily in any kind of CAD program, for example, because the only thing that you need are 2 vectors. One vector is saying, is going along, pointing along the axis, and the other one is just saying we have this axis in space. And that's it. How does it look in practice? Okay, so what does it say? Yeah, so this is what I changed this morning, so the only idea of this course, of this thing is actually to say a bit more about the using the exponential of screws in order to describe differential body linkages. If you want to know more about it, it's open X time frame. We have an extension, we have a tutorial more on dynamics, so we go that from the Kinematics to dynamics, and this goes from 8 in the morning to 4 p.m. so there's much more time. So this is, in the next maybe 5 hours, I'm going to talk about literature, this is important. I like to promote, not sure promote, but anyway, I like to mention Frank Park's book for one good reason. And the one reason is that you have two choices. You either buy it or you download it for free. So it's up to you. So it's OpenX, you can just download it. It's nicely written. What I would claim still, you can use it and you get the content you don't understand. And of course there's this Murray book and of course John Zillig's book. This is certainly a nice one. And if you want to go back to the original kind of, I'm sure it's not the first paper, but people say this is the first paper about the Euler exponential, then you can go to much of it. Huh? Oh. Thank you very much. I was saying?
No, just
fixing. Good. Yes. So let's go. Let's start with a very basic thing. And this is, I would like to describe the motion of a rigid body. So first of all, you can look at the point. I hope it's not too boring, but I think it's important to do. So you look at a point on this rigid body. So and you have a space-fixed frame, the green one. Green frame is space-fixed frame. So I have a vector P that points to that point. I can of course describe the same, or express the same location of that point, the same point, using a body fixed frame. So let's call this Q. Let's call the vector Q. Of course, and then I can say, well, I can actually express or say P is equal to R plus Q. Not much mathematics, I guess, here behind. And then comes a bit of more Kinematic or geometry at least. Because we have to say when we add them, at the end, okay, at this point I have physical vectors, say geometric vectors. And are you dealing with geometric vectors normally? You don't, because what you normally do, you use those vectors here, right? And I have some indices here, some subscripts, leading subscripts. Because whatever you do normally is you use three numbers, right? So you say this is an array of three numbers. So that's what you call a vector. Because not a vector is just a tuple of three elements. The vector would be the geometric element, the geometric vector. So, and so now you can express this vector R in a certain frame. Let's say that we express it in the space-fixed frame, F1. Whenever I express the vector R in F1, then I have a leading superscript, in this case 1. If I have the vector, whatever the vector is, Q, R, P, whatever, expressed in frame number 2, then I have a 2 here, right? So I have a leading superscript 2. Right, so then of course what you have to do, of course, is you cannot just add them if they are expressed in different frames. I would like to express the vector Q in this body fixed frame, because then it is constant. And of course the vector R is expressed in the F1 frame, and P2 is also expressed in the 1 frame. I need the rotation matrix here. So R12 is a rotation matrix that transforms coordinates from frame 2 to frame 1 in this case. Okay, this is why we have this one. Okay, this is called the point transformation. So essentially what we're doing, we are transforming point coordinates, Cartesian point coordinates, using the rotation matrix and of course the offset here, the vector R. Right, and then of course what we do normally is we put this into a certain matrix form, and this is many times this is called the homogeneous matrix, even though the matrix is not homogeneous at all, right? It just transforms point coordinates, and they are somehow homogeneous. They have to be homogeneous before we put it into one anyway. And this is fine. So, and I use C12 to describe the configuration of frame 2 relative to frame 1. What does it mean? Again, this I was saying this is the configuration of frame 2 relative to frame 1. It means that it transforms point coordinates when you measure a point, and this is why actually I'm then use that matrix to get the point coordinates of the same point when measured and expressed in frame 1. And that's why we like these matrices, because this is independent of the point. When this applies to any point, we can forget about the point that we're looking at, and we just use this matrix. And this matrix describes uniquely the configuration of the two frames. Of course, this is a long story. It's of course just saying that you need a rotation matrix and a vector. Important is that that vector, of course, is resolved in the same frame. This is the superscript 1, as the rotation matrix is transforming to. Right? So these two indices have to be the same. Okay, let's have a look at this rotation matrix. How do you describe the rotation matrix? Well, you can use triangles, but you can also use axis and angle. Let's say that we have a frame, and I would be interested in actually describing how a certain vector, let's say the vector r, is evolving in time. So let's say that initially we have the vector here, and then after a certain time t, it's here. So what I would like to do is I would like to introduce a rotation axis, and an angle, so that we get actually from this to that frame, so this to this vector. And this is Euler theorem. And the Euler theorem says that any any finite rotation can be achieved by a rotation about a certain fixed axis, and that's important, a fixed axis, and an angle. Okay, so it goes actually then. If you rotate about this vector, this rotation axis u, then that vector goes from here to here. That makes perfect sense. And this is correspondence theorem, which is an instantaneous theorem, multi-quotity theorem, so normally called. Just says that, of course, if this is not constant, there's also an instantaneous rotation axis that does this thing. I would like to have a formula for the rotation matrix using the u and the v. So a formula in terms of the rotation axis and the rotation angle. What I can say, of course, the vector is not changing length. So if the vector is rotating, of course, the length of the vector stays the same. So I can say the scalar product is constant. So the norm squared is just r transpose r, which is the scalar product. Okay. If this is so, I can actually take the, I consider r as depending on phi. That makes sense, I guess, because whenever you change the angle, and of course this goes somewhere on this circle here. But whatever happens here, so I can actually say, independently of phi, the length is the same. So I can take the derivative of the norm, and then the norm should be 0. I mean, because the derivative norm should be 0, because it should be constant. Okay? What is this? Well, essentially, it is saying it's a differential equation, first of all, right? Now, u is 1, because we said it is a unit axis along the unit vector along the axis. Okay? So if the norm of u is 1, that means that vector is 1. What about the derivative? The derivative is very simple because we know exactly what the derivative is. If you're rotating a vector on this axis, then what happens is that the direction is, of course, cross product of u and r. And that's that one, right? So essentially what I'm saying is this is 1, then we get just this, and then of course I can say this is a differential equation actually in R. Remember that we can actually have this cross product expressed in terms of a skew-symmetric matrix. I hope this is somehow known. So, and we do denote normally we have this tilde on this curve on top of the u inside in order to say this is the skew-symmetric matrix associated to the vector u. Okay, so essentially I have the differential equation dr dphi is equal to the skew-symmetric matrix of u times r. Okay, and then writing it like this, the independent here is phi. So the vector, but still depends on t. When t doesn't show up, it's a differential equation in phi. And then of course, this is something that you might remember from system theory. It's pretty simple to state here. There's a solution for that, right? Look at this equation here. I mean, this is maybe, I'll put it this way because this is possibly how you remember it. X naught equal to ax and a constant, then the solution is of course some sort of an exponential matrix exponential function, and this is the solution. And using this for that problem, you get actually the solution R phi is equal to the exponential of rotative phi times the initial value of R. And if this is true, then this must be the rotation matrix. And then what we have is actually exactly this. So we have that if we identify this has to be like this. This is the rotation matrix, then the rotation matrix is just the exponential of the utility field. Okay? Now the question is, how do you express? I mean, this is nice to write, but what is this more concretely? Because we have to actually have a formula for this. And what you can use, of course, is use the definition of the exponential. The exponential is always the same. There's a Taylor series expansion. What you do is the argument to the power of 0, that makes the identity matrix in this case, the three identity matrix, plus the same argument power of 1, and then 1 divided by the 2 factorial times the power of 2, and so on. And then, of course, what you get is like this. That makes complete sense. But we have to actually take care of this, u squared, u to the power of 3, and so on. And if you just multiply this out, then you get something, whatever it is. So this is just the square. But if you take this matrix times u to the again, what you get is actually just leave it. What you get is actually minus the norm of u squared times u to the. Okay? And that's interesting because once you have this, then you can multiply this again with u, and you get u to the power of 4, which is of course just the norm squared plus u to the squared. And so on and so on. So what you get is, of course, apparently everything, all the powers can be expressed in terms of u tilde or u to the squared. And if you collect them all together, then what you see is actually that you get here something that you might recognize. How did you recognize? I mean, what is this?
It's cosine expansion. 1 minus cosine expansion of the.
Well, what is cosine, what is sine?
This one is sine.
Yes, because the sine is an uneven function, right? So and that means we have only the odd powers, and this is the even powers. And essentially, if you look be careful, this is actually 1 minus cosine, and this is sine, and then we have this formula. So this is only known as the Euler-Rodriguez formula. Okay, this is nice. So why did I actually spend so much time on explaining it? Because I wanted to show that this rotation matrix, of course, you can derive this fluid geometrically. Maybe this is how you got the total. You have learned it, but the point is that this is the same. So we have the rotation matrix in terms of given as an exponential, and that's important because now we can say the Euler-Rodriguez formula comes from an exponential mapping. And what does it do actually? Just to repeat it, what does it do? But the Euler-Rodriguez formula transforms, because the question now is, in which frame is this E vector represented? And that's the simple exam question. There's only one frame. So if you say this one, then you're certainly 100% scores. It's that one. But then I'm asking you, okay, what is that rotation describing? I mean, there's only one frame, but there's no rotation of the frame in itself. That's the point. So that matrix, this rotation matrix, what does it do? So you plug in the E vector, resolved in the frame before it was actually moving. And what you get out is the rotation matrix that transforms from the current pose of that frame, or the body here, back to the original one. And that's an important message. So the rotation matrix, given in this form, with this vector E, is the rotation matrix that transforms from the current frame back to the original one. That is sometimes called the active interpretation, but you can also have some sort of passive interpretation by saying, okay, what is particular about this? Particular is that initially, of course, if there's no, if phi is 0, then of course this
Cosine.
That f of f star, of course, is f. I mean, there's no motion, right? What I was about saying is, if you now have two frames, the condition is that initially they coincide, right? If I use the same formula to say now I'm describing actually the relative motion or relative rotation of two frames, then of course I have two frames. This is not so easy. Then I cannot immediately say, okay, the rotation axis is expressed in that or this one. Yes, I can, because I know where this came from. And as long as I assume that F1 and F2 are overlapping initially, right? So because any exponential mapping, if you have a zero argument, what's the outcome? It's some sort of an identity. Either it's one in the scalar case or it's the identity. Same here. Okay, so what it means, initially F1, F2 coincide. What happens because after motion is that, of course, the rotation matrix, when you express the rotation axis in the frame 1, is the rotation matrix that transforms from the F2 to F1. Right? But that's important. It's just a little tiny detail, but that's important.
So you have this superscript 2 is not correct there. In the second vector, you have one E2. No, that one.
Yeah. This is a bit good. This is the square. That's the superscript. So this is okay. Here.
Okay.
So that's the thing I'm talking about. So we have the vector E1. That's the vector expressed in frame 1. And then you put this in the symmetric matrix. And then what you do, you square it. And then you're here. Okay. Right? So the other notation, sometimes people have it as a subscript. Then it's confusing if you multiply it with the rotational matrix, because then sometimes you can't really distinguish. Right? Good. Okay, so this is important. So we have this is maybe another one? Yeah, that one. Yeah. The rotation matrix, given by the Euler-Rodriguez formula, this is the only message, has an argument. This is the vector E, and the vector E is the one that is expressed in the frame, which is, in our case, the F1 frame. And what is important is that the superscript, and the first index in the rotation matrix must be the same. Okay, and that is it. So of course, we can say this is what we normally do. We say that we are rotating about one of the principal axes. So we can rotate about the 1, 2, or 3, or we call it X, Y, Z axis. Then of course you get these matrices, and then you can combine this. Either you use these Euler angles or the Cardan angles. It's just a matter. So you rotate about the 1, 2, and the 3 axis, the X, Y, Z, or you rotate about the 3, 1, and 3 axis, and you can have any kind of combination. Okay. Then you get these rotation matrices. Okay, so what we've done is, of course, describing the rotation of that body. What about the translation here? Because a rigid body is not only performing, it's not only performing rotation, but also translations. And of course, the blue line is not by coincidence. There is a meaning, and there is a good reason why I do this. You see, what I'm doing here is, I would like to know the motion that transforms, that brings actually this body from here to here. And there is a nice theory. It's normally called Schwarz theorem, that any finite is the counterpart, or say the extension of Euler's theorem. Because it says that any finite object displacement can be achieved by screw motion, by the constant screw axis. So a screw motion is just that you say that, for example here, that body is rotating about, that axis, and at the same time it's sliding along the axis. Okay? And that's normally called the Schwarz theorem. And there's of course, that's actually was actually before Schwarz theorem. What's the Cauchy theorem? It says that it doesn't have to be a constant axis. It can even be, what it says there is an instantaneous axis. So instead of saying that I'm looking for the motion that transforms from one. Okay, so what does Schwarz theorem allow me to do? Have initial configuration of a body and have a finite configuration of a body. And then I say, okay, what's the motion along a constant screw axis that transforms the initial configuration to the final one, and that's Schwarz theorem. But of course, the body can have a different motion. Of course, it can go anyhow to this place, right? It can travel around the US and then come back, and then it's here, right? And this is then about multi-Cauchy theorem, because then it says there's always an instantaneous screw axis. So even if the body is performing in any real plane, there's always an instantaneous screw axis. And this motivates us to have a look at the screw axis and to ask, how can we now describe the motion? Because I was saying that the relative motion of a frame, again, is given, or is at least represented by these homogeneous matrices. So we have the rotation matrix, and we have the displacement vector. Yeah. And we can do the same as we have done with the rotation. So I can ask, okay, I have my body initially. This is the initial configuration of my body, and then after a certain time, I have this, the body is saying, the body laying here. So it lies in some other plane or whatever. I mean, it's just moved around. And then I have two frames. Of course, the two frames are initially coinciding because I take the body and then I move it. So initially, F star is the same like F. Okay. And okay, what I have is of course the displacement vector and the rotation matrix, and I put them all together in C. And then of course, according to Cauchy theorem, Charles theorem, there should be a screw axis. So that means there should be an axis, and of course the rotation angle. Right. What about the indices now? Because I have to say, when I have two frames, F2, F1, they are initially coinciding. I have to say in which frame, for example, this R12 is expressed. Because I'm, of course, measuring the displacement relative, of F2 relative to F1. That means, it makes a bit sense, to express this vector in the first frame, in this F1. Okay? So what I have is this R12 expressed in frame 1. Okay? And this makes perfect sense because everything here, whatever comes out of this matrix, is expressed in this frame 1. See, the rotation matrix transforms from frame 2 to frame 1, and that vector is already expressed in frame 1. Good. And then, what's the difference? Yeah, this is screw axis. Okay. So the assumption is, of course, that F1, F2 initially coincide. So we know about the rotation matrix. You know already the rotation matrix R12 is given using the Euler-Rotatus formula by just two arguments. One is the vector along the unit vector along the rotation axis, call it E, expressed in frame 1, and the angle phi. Initially, of course, because they're coinciding, this is the identity matrix. That makes sense. What about now when I ask about the displacement? So what I can say, of course, is that we can measure. Let's say that we pick a point on the screw axis. Okay, so we have that point here, and well, then after the motion, for example, it's here. So I can measure the points relative to frame 1 and relative to frame 2. So this is P1, P2. Let's express them in either frame 1 or frame 2. What can I say about the relative displacement of the origins of F1 and F2? Well, this is simple because, what do I know? I mean, first of all, it's just a vector, so it's going this way. So the vector from here to here is the same like this. So I enter vector P1, and then I'm adding a vector, that one here. So what's this vector? Well, certainly it's somehow E, right? So it must be pointing along E. What's the displacement here? It's the angle times the pitch. You know pitch? So the pitch is just saying how much you're traveling along that line when you do one turn of rotation. Okay? So phi times h, if h is the pitch, is the amount we are traveling along this line. Okay, the direction is clear, this is E. So phi h E is that vector. I don't have to go this way, it's just minus P2. And then we are there. Right, but now these vectors are still not expressed in any frame. But I have to express them in a certain frame, otherwise it makes no sense for me because I have to compute with numbers. So let's say everything is expressed in F1. I was saying that we express R12 in F1. Right. P1 already is expressed in frame 1. This vector E, let's also say this is expressed in F1 because we had it already expressed in F1. What about that one? Well, this is P2. P2 normally is expressed in F2, so we have to use the rotation matrix that transforms from 2 to 1, and now you see that this has to make sense because this index here should be the same as the second index in the rotation matrix, and then what comes out should be corresponding to this one. So there's the one here, there's the one here, two here. Okay? Right. And initially, I was saying, all these frames coinciding. What does it mean? Coinciding means that for phi equals 0, well, this becomes 0. What else? The rotation matrix becomes the identity. That means that we're left with this equation. Well, that makes, I guess, sense, because what it actually says is that P1 expressed in 1 is the same as P2 expressed in 2. Okay? And just let's call that P expressed in 1. Okay? And if you sum this up, because we have this expression, now I know that this P and this P is just P. Then we have the displacement vector, R12, expressed in frame 1. The identity, that means just P, that was this one, minus the rotation matrix times P, that is this, plus that one. Okay, that's nice. What's wrong? What's the problem here? If anyone is still here with me? I was saying that this is nice because it fits. So we have this vector expressed in frame 2, and the rotation matrix that rotates from 2 to 1. So they always must be the same. What about this one? Well, just say it's not the same. Just tell it. Okay, here's 1 and does 2. Right? So 1 and 2, and this doesn't fit. What's the problem? See, the point is that the equality is only numerical. I mean, numerically, they are the same. That means if you measure measure P1 in frame 1 and P2 in frame 2, they are numerically the same. Because we are dealing here with, again, a triple of 3 numbers, right? And they are numerically the same. And this is why we can actually claim that this is correct. But only because we say that initially, these frames are coinciding. Just remember this, because we have to take care of this later on. Okay. Okay, what we are left with, or what we are arriving at, is, of course, first of all, a closed form expression for C12. So what we're having now is an expression of this relative configuration of F2 and of 2 frames, 1 and 2, in terms of what? In terms of 3 parameters. There are 2 vectors, E and P. One is the unit axis along the screw axis, and one is the vector to a point. This could be any point on the axis. And then of course the pitch. And yes, of course, probably not the vector, the angle phi, the alphabet. Right. That's nice. You can actually use these vectors to define something that is called the screw coordinates. Instead of saying that instead of saying that I use E and P in this form as I have it here, I can actually say, well, let's put them all together in a 6 vector. Let's say I put them, I have first the vector E, and then I'm having something like P cross E plus HE. I guess you have all seen this, and that's normally called the screw coordinate vector associated to the screw axis. Okay? More or less the same formula. So what we're having is essentially a formula for this homogeneous matrix in terms of screw coordinates. If we have the screw coordinates given in terms of E, P, and H. And you can actually split them if you're just interested in a bit more geometry, because this is, the first part is just what we normally call the triple line coordinates, or the way coordinates. And then the second part is just the one that gives you information about the pitch of the screw motion. Okay, and I will just emphasize this could be any point. You can use any point on the screw axis, and that's still correct. Right. What about the 6 vectors? We can actually use these 6 elements and define a 4 times 4 matrix. So this 4 times 4 matrix has a meaning, and we will see why this is quite useful. If I just use the abbreviation here, I call this eta. mean, this P equals E plus H E. I put this eta just to make life simpler. So then we have this here, and then what I do is I take the first component, the angular component, in this co-coordinate vector, and I put the corresponding skew-symmetric matrix in here. So we have a 3 times 3 matrix here. Then we have that vector that gives you all together a 4 times 4 matrix. Okay. And now what is interesting, if you do the same as we have done for the rotational matrices, so you just plug this in a exponential mapping. So you see the definition of an exponential mapping is always the same. Whatever you put in as argument doesn't mean it's conversion, but in this case it is conversion. So what we have here is the 4 times 4 identity matrix, because we're dealing with 4 times 4 matrices. And then, okay, the same. Also, by the way, we call this x hat, right? The x hat is the corresponding 4 matrix. And if you expand this, it's not difficult, you don't have time to do it, you will actually find that you get exactly the same. You get exactly the same as we have gotten before, which is the rotation matrix as the exponential of phi e tilde, the skew-symmetric matrix, and the vector r, the displacement vector, exactly as we had before in this form. What's the conclusion? Well, the conclusion is, first of all, the homogeneous matrix, where it's a C, here, is given in terms of an exponential. And now the exponential of this matrix, this 4 times 4 matrix, we call it x hat, whatever x is in this case, I mean it's called the argument. Here. Yeah. So these two coordinates, you put them into the 4 times 4 matrix, and then we put it in the exponential, and then we get exactly what we have done before. So, and that's interesting, because now we have, again, I was saying exponential mappings are nice, because you can deal with them nicely. Because you can take derivatives and derivatives. Okay, good. So what is it all about? Why is it so good actually to have this exponential mapping in terms of the screw coordinates? Well, first of all, because the screw coordinates are easily determined. You just need 2 vectors instead of 4 then in part-black ones, for example. And you can just, use any frame to express these vectors. And what is even more now, you have actually now just to use one vector P and one vector E, and you can describe the finite motion of a rigid body, okay, in terms of an exponential. And this is the summary. Okay, this is just to take note. Whenever I have this little book here, so this is something to maybe remember. So this is an interesting and useful design. And you find this in many textbooks in different forms. I like to use this for today. What does it do? This is important to remember. So we have these two coordinates expressed in a certain frame. And let's say that we express it in F1. So everything is expressed in F1. The x vector, all these components in the vector x are expressed in a certain frame F1. Then what this exponential mapping is giving you is the motion of that frame F1 after a certain period of time. Or you can put it the other way around. It describes the motion of a frame F2 relative to frame F1 when F1 and F2 are initially coinciding. Okay? Good. And there's a bit of more mathematics behind it, just because you certainly see this sometimes, I mentioned this. All these matrices, they form a group. What does it mean? Well, essentially it means that you can multiply such a vector, what's that joke, right? You can multiply a homogeneous matrix, what you get is a homogeneous matrix, right? Makes sense. And there's an inverse. That's the inverse. Multiply this and this and you get that inverse. Okay, so we have an inverse. We have property that this set of all these matrices is somehow closed, because you multiply them, you get the same type of matrix. And also we can, doesn't say here, but we can of course introduce a smooth parametrization, just as we have seen with this here. Because this is the kind of a smooth parametrization in the sense that you can take derivatives and they exist. Okay, so we have a smooth parametrization, we have an inverse, and we have a group. Having a smooth parametrization means it's manifold. Some sort of, whatever it means, it's a nice place, right? Having this group property and the manifold together and an inverse, we have a Lie group. This is just very basic definition.
You are missing one property, Andreas. You are missing associativity.
And associativity. And even this is not at all in mathematics definition. Just to, if you leave the room, you should have heard about Legos at least. And these four matrices, they also form something which is called the algebra. Essentially, it's a vector space, right? So when you take these four matrices and you add two of them, what do you get? Well, you get something that has the same structure. Because you add what you do, you have C1, C2, for example. You add them, this skew-symmetric matrix plus another skew-symmetric matrix gives you a skew-symmetric matrix. You add a vector plus a vector gives you a vector. And that's a vector space. There's a bit more to it. We'll see this in a minute, maybe. And that's why it's called the algebra. Anyway, and the important thing is that between the algebra and the group, there is this exponential mapping. So anyway, that's not important. Let's now see why this is actually quite helpful. So let's look at the position of the kinematic chain. So we talked about the lower pair joints is probably expensive. So again, let's say that we have an open chain. So we have a chain of rigid bodies, and let's look at body I. Okay. Okay. So each link gets a reference frame. So let's say that we call this Fi. So body I is now attached to the body 6 reference frame, Fi, and of course the configuration relative to the this inertia, I would say good fixed frame, is Ci. Okay, and then we know that of course this is exactly this. And I don't need to say, because normally I had two indices here, right? I should have said R01, 0I, RI, R0I, and C0I, because it is relative to frame 0. But whenever we have 0, then we refer to this inertial frame, to the vertical fixed frame, we drop to 0, we omit just 0. Good. But we can, of course, we have to, of course, to say something about the relative configuration. So we have the configuration of body I with respect to body I minus 1. And of course, this is the relative rotation of frame I relative to frame I minus 1. And then, of course, we have this position vector that points from Fi minus 1 to Fi. And I would like to express this in Fi minus 1. Okay? That makes sense, I guess. And now the obvious, probably, step is to say that, of course, if this is a relative motion due to a screw motion, because it is a lower pair joint, and a lower pair joint is always a screw, can be represented as a screw motion, then I can introduce screw coordinates. I can say there is a unit vector along the, in this case, the double joint axis. Of course, there is a displacement. I mean, I can say that the axis, the point on that axis, is described by a vector y, measured in the space fixed frame. Then I have my screw coordinates that I can assign associated to the screw motion thing. Okay? So I have the screw coordinate vector, very simple as we did before, and I plug this into the exponential, and then I have my relative motion. Okay, that sounds good. Was too much. Yeah, so done. Okay, so that's good. So what do I get? I have the possibility to describe the relative motion of Fi relative to Fi minus 1 using an exponential, and the argument of the exponential is just the screw coordinates of this joint. Right, and I can use this now successively to describe the motion of each of the links in a open kinematic chain. So let's say I'm interested in whatever I means, some body C, some body I, or some link number I, and I would like to see how the configuration of this link relative to the space fixed frame F0 is expressed in terms of the exponentials. So what about the first joint? So let's see what happens. The first one, actually that one. So this is the first one. So how many joints do we have here?
20?
No. 1, 2, 3, 4, 5, 6, 7. It's a so-called anthropomorphic arm. Why is it anthropomorphic? How many degrees of freedom has your arm? Huh? Well, normally infinite because it's a continuum, but normally it's 7, sorry. Right? Well, this is why it's called anthropomorphic arm. It's also kinematically redundant because normally you need 6 degrees of freedom to position thing in space, right? But you have 7. Okay, so what happens now? First part. What happens? What's the motion of that link? I mean, if I transfer the link due to the first joint motion. What is it? Well, it's of course that, right? That's what we said. The motion of body 1 relative to the predecessor, which is the ground, is exactly that. What about the next one? What about the motion relative to the second joint? That was number 1. Axis goes in this direction. Number 2. What about the second one? Well, it's just the same. And then I can combine them, right? Because this is the, okay, good. And then I go up to the, whatever the I is, up to the link I, the joint I. And then I need something, because what do I get here? What is which motion am I describing here? The motion of which frame are we describing with this formula? Okay, other question. What about Q0? If you put Q equal to 0, what do you get? Identity.
Initial position.
That makes little sense, I guess. Because whatever the frame, let's say we have the end effector. So let's say the end effector, we have the frame. Here's a frame. This is my end effector frame. There is a gripper on it, or I don't know. Okay, so if this formula gives me the identity, that means that initially it's here. Now it's here. That's not really what I want. I need to have some constant offset, right? And that's exactly this absolute, I call it absolute reference configuration of the respective link. In this case, link I. Okay. And that's what we call the product of exponential. Okay? And the pose of the body I now in the kinematic chain is given by this product of exponential. The only thing you need are this, again, the 2 vectors that go into the screw coordinates and the absolute relative configuration. And I would like you to make sense of this formula. There's no listening tonight? But first of all, I mean, I would like to help you. Did anyone understand what I'm talking about? Did anyone understand this? I guess you got the basic idea, right? But you did not understand it. So let's make a little bit sense of it. So what I was saying is actually, look at this. This is a remote center of mechanism. Whatever it is, it's a mechanism. So we have 1, 2, 3, 4, 5 joints. That is essentially, this is for minimally invasive surgery, right? So what you do, you have an instrument that goes in here, and these axes there are, I mean, which one? This one and that one, and actually, if you have an insertion, whatever, surgery instruments, whatever it is, pointing here, they're all meeting in one line. So essentially, this could be somewhere here where the lines meeting. It could be the insertion point in the body, so that's right. So let's see what happens here. So what is the motion of? So there's one advantage of using the theory in this case, and in the form we have been using it, which is that we only need one frame. This is a space fixed frame to express the screw coordinates of the joints. And this is the biggest advantage, because you don't need body fixed reference frames or joint frames. You just need one frame, and this is the inertial frame to describe the geometry and the kinematics of the joints. And then what is this exponential mapping doing? It describes actually the motion of a frame that is initially coinciding with the frame in which we express the screw coordinates. Again, so we're expressing the screw coordinates of the first joint, for example, that's the first one, right? In this inertial frame. Right? What's then the first motion doing? So the first motion, I mean, that joint is moving right now, is what? It's doing, what is this exponential mapping doing? Yes, it is actually expressing how this green frame, because it's green. Why is it green? Because that link is green. So the frame that is attached to the link to the green link, to the first one, which is initially coinciding with the inertial frame. Right? So this is what the exponential of the screw coordinates of the first joint are doing. And that makes perfect sense, I guess. What about this second motion? I mean, the motion of the second joint is one. That's the second joint. What happens now? Well, essentially the same. So essentially what happens is that it describes the motion of the frame that is attached to the blue link, the second link, due to the motion of the second joint. But, okay, which is initially coinciding with the green frame. Okay, do it again. So what I'm doing is, this is the motion of the, if it's coming, okay, this is Microsoft. Yes. Once more. It's actually restarting automatically. At least they learned how to cope with pressures. Right. Okay, there we go. So, okay, that was it. That was the first motion. And now again, sorry for the interruption. What was what was the effect of the motion of the second joint? It is actually telling you how the frame that is attached to the blue link is moving relative to the green frame. Okay? There you go. Now my question, what about the screw coordinates? These screw coordinates, in which frame are they expressed? Now there's a bit of a contradiction now, right? Because these screw coordinates, I was saying there, all the screw coordinates are expressed in the space-fixed frame, in the gray frame. But apparently, if this is true, what I've been saying, that the motion of the second joint is actually saying, describing the motion of the blue frame attached to the second link relative to the green one, which is attached to the first link. Well, there's a discrepancy. So which is now correct? Everything I'm saying is correct by definition. Essentially because we say that initially all the frames are coinciding. They are numerically equivalent. So you can, and this is true, it's absolutely correct to say that all these screw coordinates, all the vectors that I need to describe the motion of the joints are expressed in the inertial fixed frame. But the physical meaning is, of course, that the motion is always relative. I don't know what happens here. The motion is always relative to the gains. I don't know, that's working. But the motion is always relative. Now I lost what I'm saying. It's always anyway. So, but still, the motion of the blue is relative to the green, described by the screw coordinate, by the finite motion given by the exponential of the screw coordinate, which is expressed in, and this is now important, expressed in the gray coordinate system, which is initially the same as the green coordinate system. This is why this is the same. And now you can say, you can use the same argument, and you can of course go one step further, and you say, what is then the effect of the, what is now number 3, the third motion, joint motion is the same, and then you can of course proceed, and then you say, of course, it's always the same. But it's important to understand that it's always the relative motion of frames that are initially coinciding. And this is why we can always use the space-fixed frame to express the coordinates, the screw coordinates. And that's the important thing, because you don't need to introduce frames, lots of frames. You have only one frame. But now is a problem, because actually I'm not interested in the motion of that green frame. I'm interested in the motion of the antiframe, for example. So there's something missing. I always stare at you because you're kind of following, I'm sorry. So, and also I'm not interested in the yellow one. I'm interested in this end vector frame. And this is why we now need actually the last step, and this was this A, the absolute, this constant offset. Because at the end, what I get out of this exponential formula, right? This times this one times that times this times this times this is the motion of the yellow frame relative to the gray frame, the world fixed frame. And this is what I am not at all interested in. I'm interested in the motion of the end effector frame, this one here. And that's what I need, and this is of course they are on the same body, right? So the yellow one and the red one are on the same body on the end effector link. So the only thing I have to do, because they are on the same body and this is a rigid body, there's a constant offset, a constant transformation. And that's called as A5 because this is bless you. And this is link number 5, and that's why we say this is the, and now again, this sounds to be a contradiction, this is the absolute reference configuration of link 5. Why can I say this is the absolute reference configuration? It's just the reference configuration of the two frames on the same link. Well, very simple, it's always the same argument, because initially everything is coinciding. So if I know the reference configuration of my end effector frame, which I'm not showing here, the red one that was here, relative to the space fixed frame, which is identical to the yellow one that is attached to the fixed, to the link, the last thing, then of course I have it. And I have of course the same, because this is constant, because it keeps going. Yes, it keeps constant, and at the end what you get is of course exactly is exactly the same. So, and then of course this makes sense, and at the end you get really what you want to know, and this is the configuration of this end effector frame relative to the inertial frame. So I hope this makes sense. So if it makes sense to you and you have the feeling that you understand, you can go to Disney World tonight. If you are interested in actually doing it, then you can go to the website and you can download a mathematical package, and you find a couple of things. And I have this here. So I use Mathematica. I'm not sure if the Mathematica is something that you are familiar with. Who knows Mathematica? Who knows Maple? Okay, two questions. Who knows Mathematica? 1, 2, 3, 4. This is pretty good. Who uses Maple, for example? I'm surprised. Good. Okay, so that means that 20% don't use neither Maple nor MATLAB or any symbolic. That yes was what? MATLAB. But that means that you're not using symbolic manipulation. Computer algebra software. What? Yeah, this is not far from Mathematica, I guess. Huh? Yeah. This is just cheaper, eh? Yeah. That's free, yeah. Anyway, so it's all the same. You find this on the website, and you can download. And just this is, I mean, the most probably simplest example you can find. It's a 2-hour mechanism, so it's a planar mechanism. So you have 2 Robotics joints, and I would love to just show how this goes. If you go back maybe into the slides, and of course what we need to do is, what do we need now? So I would like to describe the kinematics of this thing, of the open check. We have 2 Robotics joints here, and what we need, of course, are the screw coordinate vectors. What do I need? I need the unit vector along the joint axis. Well, this is simple. I have this. So this is my space fixed frame. So this is 1, 2, 3, or depends how you call it, x, y, z. So the axis, the unit axis goes along the z-axis. That means 0, 0, 1. What about the y, the position vectors? 2 points on the axis. Well, I located actually the reference frame on the axis. So this is the joint axis, the first one, and of course the position vector to any point on the axis is 0. Second one, so the joint axis is here, my frame is here. What I can say is I would like to use the point that is actually here. So this point, the axis is here, and I use this point on the axis to and measure this, and this is going along the x-axis, and this is the length of the first link, which is L1. Okay? So then we have almost everything. And by the way, h is 0 because it's a dominant joint, there's no pitch, h is 0. And if you do the cross product, then you get exactly this. This is of course very simple. And the cross product of, what is it now? That one, this one, is this one. Okay, then that's almost it. But we need one more thing, which is the what? The absolute reference configuration in the zero reference configuration. So zero reference configuration is just when Q equals 0. So where is the frame F1 initially? Because what you're seeing is the initial configuration. So where's F1? Well, F1 we need two elements. One is the rotation axis, and as you see, you hope you see it, they have the same orientation, so this is the identity matrix. But there's a displacement, and the displacement is L1 half in X and A in Z. L1 half and A in Z. Or you put it if you want like this. What about the second one? The second one is same. It is the height is B, so it's in Z, it's B. And then it is of course the length of link 1, half length of link 2, it's exactly this one. Okay, and then you can do the formula and then you get it. And let's do this in practice. So there's a package, you just have to say where it is. So the path, just the path where you have it on your drive. And it's called, I just called it Higher Order Kinematics KISS 2019, so you get the package from the website. Yeah, and there's always a bit of a warning because there's always a change in the mathematical version. So what I do is I define, of course, just the vectors. So this is how you define vectors with the brackets, and then the other ones, and then this is the first function that we use is screw vector. Two arguments, which is the vector, the unit vector, and the location vector, and then you get this. Okay, and then this is almost it. Then we have the reference configuration. This is the same. So there's a function that's called cos to SE3. So I was saying that these homogeneous matrices, we call them SE3, and what it does, it takes the rotation matrix and the position vector and it puts it into this matrix, and then it proceeds, and then we go one step further. Then we say that it's a function which is called SE3x. So this is just the exponential on SE3. So you have two arguments. One is the screw coordinate vector, y1, and the joint, the variable that we have there. In our case, we just call it Q1. This is the first angle. Okay, and then this is what you get. And the question is it correct? Well, first of all, we have the rotation matrix. If you take a bit of time and you contemplate and beer or whatever you want, then you see this is a rotation matrix that describes the rotation of the z-axis. You see this because you have the one in here in the 3-3 component, and then it's just a planar rotation. What about the displacement? Does it make sense? Does it make sense? So how does this plane, what's the position of the origin when you rotate about this axis, the Q1? Maybe it makes sense because what you have here is half L1 cos Q1 and half L1 sine Q1. That should make sense. Well, I guess you see what that means. Okay, what about now the second? What is it? The second. So I would like to know the motion of the second frame. So rotation matrix, certainly not so difficult. It's just, again, a planar rotation. So that's the same. Just the sum of the two angles. What about the, maybe look at one. What about, let's look at the final version. So this, I guess, makes sense. I mean, yeah. So what is it? It's back and forth. So what you have here, you have L1 cos plus half L2 cosine Q1 plus Q2. And I think this, if you have a bit of an understanding, that makes sense. But I would like to emphasize this only makes sense if you multiply with A2. But maybe have a look at this here. So I just combine the two exponentials actually. So if I combine the two exponentials, I get, of course, quotation matrix. But see what I get here. What is this displacement? So this is the displacement of the origin of the frame. But maybe this is not the frame that we have here, because probably this is not the frame. So which one is it then? Maybe you don't see this here. It's not so obvious, but I was actually telling you what that is. What is the motion of the exponential of that joint combined with this one without this A term at the end? What is it describing? I see you didn't follow me. Again, this is the motion of a frame that is initially coinciding with F0. Right? So what you get with this formula, x y1 times x y2 is exactly the motion of the frame, of a frame, attached to link 2, initially coinciding with F0. Remember that movie? Right? So it's essentially the one that is initially here. And maybe this makes sense to look into what happens if we have Q. Yeah, of course, yeah. If you put Q1 and Q2 0, then of course we get 0, right? So it's telling you actually this is the one that is initially here. And then it's moving somehow attached to the link. It's moving out of the plane. Okay. Okay, then we can do some more. And there's a Jacobian. We didn't talk about Jacobians. Yeah, we have to do this. Homework. If you want to do this, I mean, this is very simple. Look at this. Now I can actually explain what that means. This was the remote center of motion mechanism. So, because essentially this is a kind of a spherical mechanism. If you want to model like this, and then if you fix the first part, then imagine that your body is here. I mean, maybe not yours, but someone. Body is here, and then you have this insertion point here, and what the doctor is doing, it fixes actually the first part, and then you can move it around and you know, do whatever is to be done in your body. So let me come back to Delavier-Tartan mathematics, because we have been saying that maybe this is better than Delavier-Tartan mathematics, I'm not sure, but maybe it is, because I mean, this mechanism is maybe not the most complicated in the world, but you see that with Delavier-Tartan this will also be simple to do it, I guess, because everything is varied. But what you need here is also very simple, because you need only the vectors, and with all these distances here, you can actually very easily find all these vectors, and then you can input this. And you find this in the other worksheet on the server. So, and we like to actually do this kind of things here. We have the fastest coffee in the world, by the way. This is kind of an optimal motion, and we have coffee in here in the intersection. It depends on the occasion. Sometimes red wine and Red Bull. And so what happens is that we have this industrial robot. It's mounted on a linear axis, so we have 7 degrees of freedom. And it allows us, of course, to slide along this while the whole system is moving. So, and you can also use this for catching balls, for example. Right? So there's the guy throwing a ball in it, and then have it online. And you can imagine it's not that easy actually. Anyway, what we need is our models. So, and again, the model that we need here is of course very simple. And now if you look into this example, maybe the dynamic parameters are not that easy in this case. And also the description. But if you use this, the approach that I've been showing, it's very simple because we just need the unit axis, and let's say that we have the initial configuration like here, so the arm is stretched upward, and the only thing you need are the position vectors of the points. So these dots are the axis, I mean the joint axis, and then the only thing you need are displacement. So let's put the frame, the reference frame in here. Then what we have, of course, are certain displacement. So we have there's one in x, and there is one in y here. Missing. Yeah. So and that's what we have. And then of course when you have this in here, I mean it's just adding up these things, and the reference configuration and the initial configuration is just the identity because we just put the axis on the links in the same orientation as we have the inertial frame. Yeah, and then you get it. It's all on the server. Yeah, and then of course you can have the spherical mechanisms, and it's also very simple because what you do here is probably very simple. The most simple is when you put the reference frame in the center of in the point where all the axes meet, which is the center of the center of motion of the spherical mechanism, and then of course all these vectors along the to any point on the to a point on the axis they vanish, and then you just have the unit axis, and that's pretty simple, and that simplifies it further. Okay, and so what we have at the end is of course a nice description of the forward kinematics also of a serial manipulator, of a robotic arm in terms of the screw coordinates. Right. But sometimes we are interested in actually what happens if there are deformations. What happens if there are certain geometric parameters, like some of these links are somewhat deformed, or there are misalignments of joint axes and so on. What happens then? And then maybe that formula is not the best one, because all the joint screw coordinates are expressed in a space-fixed frame. And sometimes it makes sense to express them not in a space-fixed frame, but in a body-fixed frame. Because then you can, if it's expressed in a body-fixed frame, you can easily describe these misalignments and even deflections. And this is why there are different versions, and without going into detail and without explaining it, you can imagine that if these relative motions are expressed in terms of screw coordinates that are measured in the inertial frame, you can also just use a different frame, because the inertial frame, I mean the work-fixed frame, is arbitrary. You can use any other frame. And we can also say, okay, if this is so, then I can use a body-fixed frame to express it. The only difference is, then of course I have to account for the constant offset with a certain matrix, and this is B, I call this B, for body-fixed reference. Yeah. And that's it. So what about closed-loop systems? Let me say a few words. I mean, what a closed-loop system is like a closed loop, a kinematic loop is something like this. Okay, you just get it open together somewhere. And we know how to describe actually the motion of the chain if you cut it open. So let's say that we cut the loop open, and then we have here's number one here. So we have joint 1, 2, 3. Up to n, and then we can describe the motion of this open chain, of course, using the one of the exponentials. And the only thing that we need, of course, is screw coordinates of the joint axis. Okay. What's the condition? Okay, what is this? If you say that we have this mapping, because we can combine now the relative motions of the Newton joints. And what is the condition? Because there must be a condition, because otherwise it wouldn't be closed. So what is this function, what is this mapping here describing?
Must be the identity mapping.
It must be the identity mapping. You know better than anyone else because, yeah. Come back to this later. So what is it describing? It describes actually the motion of a frame that is attached to this virtually, because this is only virtually open, right? To the other half, virtually open length. No, I'm lost. So what does it do? So we have what's number one. So here's number one. So there is a frame. Let's say there's a frame here. This is our reference frame. Okay. So what is it doing? It is actually describing how this virtual frame of the open chain is moving because in reality it cannot move because the closed kinematic loop. This must always be the identity. So any admissible configuration Q must actually be such that whatever comes out of here must be the identity matrix, right? So and this is another application of this POE, of this product of exponentials, because now we have this mapping, and this gives you the constraint mapping, right? So this is essentially the mapping that gives you the loop closure constraints in terms of this group coordinates, of course. And yes, Federico, of course, is one of the earliest person who started looking into this, because now the question is, you can ask many questions now. So once you have the constraints, you can ask, okay, so what's the solution set? Well, that's great. I mean, it's really different. I mean, closed form solutions, but this non-linear equation, forget about it. But the most simple, but not easy question is, what's the dimension of the solution set? Why I'm interested in the dimension of the solution set? Because this is the mobility. Right? So if I somehow be able to actually define or determine the dimension of the solution set and know about the mobility, then the question is, what mobility? Finite mobility? Yes, that would be the finite. But then again the question, there are mechanisms that can change mobility. So which one is it now? And so on. So once you start in this, so this is the configuration space. And then of course the dimension locally, the dimension of this space, we call it V, this is just a variety, is of course the local So, and of course there are multiple linkages, and then what you have to do is you have to consider the loops. But how many? Well, you have this funny mechanism here. So how many loops do we have? We have two. But we can say there's one here, and there's one here, for example. So that means in this topological graph, you would, the vertices are just the links. So, 1, 2, 3 points up. And the edges are the joints. Okay? So what you can say, there are two fundamental loops. And this is a bit math theory. Very simple, but anyway. So how many fundamental cycles do you have here? Two, I was saying it here. And there's a number. This is called the different names, the Euler number or the cyclomatic number, whatever. So the number of fundamental cycles is unique, but they are not unique, because I can also use that one, these two. Or I can even, whatever. But for each of and the same here, you have this PKM, this parallel kinematic machine. So how many loops do we have here?
2 again.
What? 2 or 3?
Well, fundamental 2.
Yes, 2. Right. So for example, these two. But I can also have, for example, the orange one and maybe that one. Anyway, so I'm just mentioning, so what you have to do is you have to formulate the loop equations for each of these fundamental cycles. So that's one sense. Right, and I guess this was almost it, right? How much time do we have?
10 more minutes.
10 more minutes, perfect. Because so far we have looked into positions only, but not in velocities or twists. And that's important. And before we actually able to do this, we have to say something about the transformation of screw coordinates. Because remember that we had these four matrices, and they have been doing what? They have been transforming point coordinates, right? So you measure the point coordinate in one frame, question is, how is this point coordinate measured in another frame? And this was the 4-4 homogeneous matrix. So, but also these, but the frame transformation also describes
Line.
correct. When you express a line, for example, right? You can express a line using the Euler coordinates, the Rietz's coordinates in different frames. And yes, there's a bit of a derivation. I have no time to do it. At the end, what comes out of this derivation is, of course, just what we know. That is, we have the 6-6 matrix. So let's say that we have the transformation from one frame to the other with this again with the homogeneous matrix, R and R, I mean the rotation matrix and the displacement vector. Then the corresponding transformation of screw coordinates is just the 6-6 matrix here. Whatever. Message is there is just a matrix that transforms screw coordinates. And this is normally called the adjoined transformation. Adjoined just because it is adjoined to the point transformation. Okay? Good. And we like to use this base fix or the spaceship twist. What is this? Again, this is a 6-tuple, so we have the 6 vector. The first three are the angular velocity of the body, and the second 3 vector is the translational or just the velocity of the origin of the frame. Now this is interesting because this is something that not everybody is familiar with. Because it's a final definition. What is it? I mean, this is probably the simplest one. The angular velocity is just what? It's the angular velocity of the body measured and resolved in the world fixed frame. So you measure the angular velocity in the space fixed frame, and that's it, and you resolve it there. But what about this velocity of the point? Because now we have this translational velocity. Apparently there's only one frame here. So what point are we measuring? Well, so the point is that, and this is the definition, definition is the same. This is the velocity of a point attached to the body that is momentarily, instantaneously coinciding with the origin of the space fixed frame. Right? And because it is always instantaneously coinciding with the origin of the space fixed frame, I don't need any other frame. And again, this is very advantageous because we only need one frame. How do you express this? I mean, how do you measure this? What is this exactly? So let's see. So what we have is, of course, we have a space fixed, we have a body fixed frame because the body, of course, is represented by a frame. Right? This was Fi. Okay. And then we have this homogeneous matrix that says how this frame is relative position to the origin of the, or to the inertial frame. Right, so we have this displacement vector, Ri. What is then the velocity I'm talking about? So the velocity I'm talking about, the velocity of the point fixed to the body that is momentarily coinciding here is of course what? It's two components, which is of course, first of all it is R dot, so it's a time derivative of this vector R. But this is not what I'm talking about, because this would be the velocity of this point. Well, I'm talking about the velocity of this point. So it is that one, I mean this is R dot plus the one that is due to the displacement of the vector and the angular velocity. So it is actually the displacement plus the angular velocity, because due to the angular velocity and the displacement, the velocity of this point here, so this is the angular velocity, and I'm asking about the velocity due to the displacement is exactly the cross product of Ri and omega I. And that's then the velocity we're talking about. Right. We can actually find this in a different way by saying that I'm looking into, so we have the 6 vector here, right? And then we have been saying that we can transform all the 6 vectors in 4 matrices. What's the difference? The difference is that I take this omega vector into a skew-symmetric matrix, and I put this in here. So I have this 4-4 matrix, where the 3-3 matrix here is just the omega tilde, so the skew-symmetric matrix. And it turns out that you can actually define this as the time derivative of C times C inverse. And this may look familiar to you, because how do you define angular velocity, for example? Well, let's multiply this out. So let's see what we get here. So, okay, we have C dot, and then we have the inverse. So I was saying that the inverse looks like this. That was somewhere at the beginning. Okay, so multiply it out. What you get is R dot times R transpose. And this guy. What is this? Well, you maybe have seen it. This is the definition of the angular velocity then. So this Quotation matrix, omega tilde, is exactly R dot times R transpose. Does it make sense? Does anyone know what I'm talking about? Angular velocity, Quotation matrix. Good. That's here. It's here again. So if this is here, then we can say, okay, this is omega tilde, this is omega tilde too. So what was the property of this matrix? Well, essentially, this is it's also called the screw product matrix, something like this, right? Because what you do here, if you have a vector tilde times another vector, it's the same like the cross product of two vectors. Okay? So this is essentially the cross product. This is omega cross R. Cross product is skew-symmetric. If I swap the arguments, I get a negative. Okay, so I'll replace R and omega, I get a negative, I get plus. And that's it. Because then I get exactly what I wanted. I get the cross product, omega plus R dot, that's this, and then I get my omega. So you see, that makes amazing sense. Okay? Good. What about, that was one body. What about now if you say that we have a chain, a kinematic chain? Well, then we can have the same argument as we did before. So, okay, let's just look at what happens when we have one joint moving. So that one. Let's say that we, so I'm interested in the so-called spatial twist. That means the twist of the kinematic chain due to the motion of all these joints. So let's look at what happens at joint I. Okay. Same argument. Omega is clear. So if you, okay. What was the contribution of that joint to the omega vector, to the angular velocity? Well, it's simple. It's E times Q dot. That's this. This is omega due to the motion of that joint. Okay? Expressed in F0, as you explained. What about the contribution to the translational velocity? Well, the same as we had before. This is, of course, omega cross the displacement, or displacement cross omega. So it's SI cross omega. So omega was E times Q dot. And if there is a pitch, of course, then of course we go traveling along this with the Q dot and then over. So, good. What about the other joints? We just add them up. These are vectorial quantities. We can add them because they all express in the same train. So we can just add them. And that's fine. So what we have here is something that we can permeate with, for example, S1, S2, Si. And we can put them all together in a matrix, and this is simply the geometric Jacobian. So what we have is that the twist of the body I, that one in the kinematic chain, is given in terms of the instantaneous screw axis. Because see, the expressions here are exactly the ones as we had for the joint screw coordinates. Remember the y's. That's all the same. The only difference is that now we are in the current configuration. It's not in the initial configuration, we are in the current configuration. Because the E and the S, of course, they're moving in space. I mean, they're moving when the system is moving, right? They're different at any instant of time. Anyway, so that's why they are the screw coordinates, but in the instantaneous case, instantaneous screw coordinates. Okay, so how do we get from the one VI, because initially we have measured VI, YI. So YI, this was in the reference configuration. And now we want these in the current configuration. How do we get them? Well, just transform them. Because we know exactly that these and these are related by Fourier transformation. So these are in the initial configuration and these are in the current. So how do we get this? Well, we know this was this 6-6 matrix. So the 6-6 matrix due to the motion of the preceding joints. Right? So essentially we have the SI given in terms of this constant screw coordinates that we had in the beginning, and the transformation due to the motion of the preceding joints in the chain. And that was it. So and then we have closed form solution for the geometric Jacobian. Yeah. Right, so the geometric Jacobian, this is it. So altogether what we need for the product exponentials, I mean for the position kinematics, we need the incidence co-coordinates, very simple. For the Jacobian, we need again the co-coordinates in the reference calculation, but transformed, of course, in the current conversion. And this goes via the 660. And you find all this on the notebook. If you have questions, just let me know. The message, the take-home message is, it's a very neat and simple way of describing kinematic chain by using very simple vectorial data. And you can get all this data, for example, from a CAD product. You can get all these vectors, for example, from a CAD product without going to any parametrization method. And there are 100 more slides, which I'm not bothering you with. Thank you very much so far.
Thank you. All right, so since we don't have a whole lot of time for questions, I'm sure we can never get enough of the screw theory and product exponentials. This is fantastic stuff. By all means, catch Professor Muller and ask him your questions during the break. And we are going to we have already made the slides available, so if you want to see further, there's probably more material than what you've covered here in the slides.
Oh, yeah.
Right? Yes. Okay. And there is another workshop tutorial by you tomorrow, which they won't be able to attend, of course, because they'll be here.
Oh yeah. I should make it.
Yes. Yeah. Okay. All right. We'll take a break, and then we'll be back here at 3:30.
Yeah, I was saying that.
I don't do it, that's why.
So what did you say? I'm sure you get some copy of it.
Yes, I made all the